picking up good vibrations.
So next example is computing the Fourier transform of a two-sided exponential, so which is defined by this, and in a compact way, exponential of minus a absolute value of t, where a is larger than 0. So again, we're going to plug in this expression here, and now we see that it's defined differently when t is negative and when t is positive. So we're just going to partition this into two integrals, from minus infinity to 0 and from 0 until plus infinity. So we're going to get x j omega is going to be the integral from minus infinity to 0, and in this integral I can use this expression here. So it's e to the power of a t e to the power of minus j omega t dt plus the integral from 0 to plus infinity of e to the power of minus at e to the power of minus j omega t dt. Now, this integral over here we have just computed in the previous example and is equal to 1 over a plus j omega. So it remains to compute the first integral. Now again, using similar tricks, we see that this is equal to e to the power of a minus j omega t. We need to take the primitive, so it's going to be equal to 1 over a minus j omega e to the power of a minus j omega t, and we have to evaluate this at minus infinity and 0. And then we get plus this term over here, which is 1 over a plus j omega. Now, evaluating this when t converges to minus infinity, since a is positive, again we get a complex number whose magnitude is decreasing as t goes to minus infinity. So in this, when we replace by minus infinity, we get 0, and we replace by 0, we get 1. So we get 1 minus 0, which is 1. So basically we get 1 over a minus j omega plus 1 over a plus j omega. Now to write this in a more friendly way, I'm going to multiply the numerator and the denominator of this first term by a plus j omega, and this second term here I'm going to place by a minus j omega, so that when basically it's the complex conjugate of the denominator, so that we get a real number in the denominator, and that's because we have this property that a minus j omega times its transpose will always give us something real, and in this case it's a square plus omega square. Okay, so we're going to get twice in the denominator a plus omega square, a square plus omega square. In this first case I'm going to multiply by a plus j omega, so I'm going to get a plus j omega over a square plus omega square, and in this case I'm going to multiply by a minus j omega, so a minus j omega over a square plus omega square. We have the same denominator, so this will cancel, and we end up with 2a over a square plus omega square, which is the Fourier transform of this signal. Now, very important, since this signal that we started with is an even signal, the Fourier transform is purely real. So we can plot this Fourier transform as a function of frequency omega, and we just need to consider the real part of it right now.